beautiful downtown Raleigh. It's the Science Café with your host, Brian Mallow.
All right, yay! Hello! Welcome to the Daily Planet Cafe here at the North Carolina Museum of Natural Sciences, and it is Science Thursday, which means this is our Science Cafe. And of course, what other topic could it be tonight but Pluto? A program that's been 10 years in the making, or 85 years in the making, if we want to go all the way back to the discovery of Pluto. But so much excitement. I don't know, when's the last time America got this excited about any planet? I don't even know if we got this excited about Mars, because when we were landing landers on Mars, it wasn't the first time we were there. And so this was a pretty unique mission in a lot of ways, and it's information that, well, it's the farthest object that we've studied this closely. So everything else, telescopes got us better. Like, we had way better images of Mars before we sent spacecraft there. But what we had of Pluto was very little, and you'll see exactly what. So I'm not going to waste any more time, just to say that we'll introduce our speaker. He'll give about a 20-minute presentation, and then the rest of our program involves your questions. And tonight, we also, something that we've been doing for the past couple years here, something we've incorporated in some of our programs, there is a group of local poets called Living Poetry, and they do poetry readings and they have events, but they've been doing events here. We've had science cafes dedicated to science poetry, but what we've also done a few times, and we've really liked this part, is we've invited some poets to be here for our program. They're sitting over here. We have 4 poets, and they are going to write poems during the course of tonight's program, inspired by the program. And so at the very end, when we're done with our speaker, we're going to hear 4 poems that were just written during the past hour. So we have that to look forward to. And with no further ado, let's meet our guest. He is an engineer, and he is a JPL NASA Solar System Ambassador, and he's here to tell us all about the New Horizons mission that just 2 nights ago made its closest brief flash by Pluto. So how about a nice round of applause for Sean Bale?
Thank you, Brian. Thank you, everyone. Well, I want to definitely thank you in particular, because what we're doing today is making history together, both from a scientific perspective. This is the furthest we've ever been. It's also a great patriotic moment, because this is a time when the United States can say that we are the one and only nation that has actually explored every single major body in the solar system. Pluto was the last. So we're quite proud to be Americans, and we're quite proud of the science that we're doing. So as we make history today, we're learning a lot every day. Yes, Pluto was just visited a couple of days ago, but that doesn't mean the mission is over. The memory of that spacecraft is chock full of all kinds of very interesting data. As we speak right now, it's acquiring more, and it's going to take about 16 months to get all that information back from the spacecraft. That's how much it's actually acquiring as it goes. So we titled the talk, Pluto, Enigmatic. Why would we call Pluto enigmatic? Well, I think partially one could say that it's captured the heart and soul of the public, not just the scientists. But it's also got a bunch of very interesting facts. First of all, Pluto was discovered by accident. Back in the day, in the early 1900s, Pluto was called Planet X. We had some gravitational data that suggested the existence of a planet outside of Neptune's orbit. It actually turned out the data was wrong. We had the mass of Neptune wrong. So there was no Planet X, but lo and behold, there was Pluto. So Pluto is an actual complete mistake, so to speak, a surprise. Furthermore, Pluto breaks all the rules, if there were such a thing as rules. And first of all, Pluto is in a highly inclined orbit. It means it doesn't do what all the rest of the planets do. All the rest of the planets go around the sun in a basic plane, almost like circling around on the tabletop. Well, Pluto doesn't do that. It actually is on a 17-degree angle. So that makes it different from all the other planets. Secondly, it rotates on its side. So it actually is not rotating like the Earth. If this is the plane of orbit, the Earth is like this, Pluto is actually like that. And its moons are going around it in that direction. So that's very different from what you see in most of the other major planets. Interestingly enough, it's also highly eccentric in its orbit, which means not that it's an eccentric type of person that lives on a hill. It's actually eccentric in the sense that it spends many years, about 20 years of its orbit period of the sun, inside the orbit of Neptune. So it actually crosses inside. It's closer to the sun than Neptune. And it's also the only example we have of what we call a double planetary system. In other words, Pluto's moon Charon is about the same size, about half the size of Pluto. Makes it huge relative to Pluto. To put that in perspective, if our moon was that big and you looked up in the night sky, that would be about all you'd see. It's very, very large. And what that means is that it's not that Charon, the moon of Pluto, rotates around Pluto, it's that the two of them rotate around each other, which makes it very different. And I think if you look at this eye chart of a graph, what you can see is exactly what I'm talking about. What you've got is this highly inclined orbit that Pluto's on, and you can see how it's inside of Neptune's orbit. So I kind of call Pluto the bad boy of the solar system. Moms, this is not what you want your kids to do, okay? But interestingly enough, early on, the name Pluto came from a Greek god of the underworld. So I guess we must have known Pluto was a bad boy long before we met him, right? And interestingly enough, that particular god had the habit of being invisible, which even to the Hubble Space Telescope, Pluto looks almost invisible. So I think it was a bit of foreshadowing. And lastly, we did officially classify Pluto as a dwarf planet. That kind of upsets some people. There's a raging debate, which we welcome. We think that debate should continue. And interestingly enough, I would like to modify that statement and just say that based on the data we have from New Horizons, we can officially claim that Pluto is the king of the dwarf planets, because we've now proven its size, so we know it's bigger than anything else we found out there. So being the king of the dwarfs isn't such a bad thing. So let's talk about some facts about Pluto. It was discovered in 1930. It is the only planet that was discovered, or dwarf planet as the case may be, that was discovered by an American astronomer. And it was discovered out of an astronomy lab out in Arizona in 1930. In addition to that, it takes almost 250 years for Pluto to get around the sun. So, folks, it's a long year. It's a really long year, and it gives rise to some interesting science we can talk about later. In addition to that, Pluto actually is tilted 17 degrees to its orbital plane of the rest of the planets, as we said. It's a highly elliptical orbit. Notice those numbers, 2.8 by 4.6 billion miles. That B means billion. This thing is really far out there. That's why it's so hard to see. And you can see that makes it an average about 3.7 billion miles away from the sun. By the way, think about how hard it is to get a spacecraft to a planet that far away. It's not a trivial task, and that's why we call it rocket science. So, Pluto, as we mentioned, rotates on its side, but given its size, it actually only has gravity about 6% of the Earth. So that makes it, almost like an asteroid in the sense that its gravitational field is very, very weak. And I think you should bring your coats, folks, if you're planning on going camping here. Minus 387 degrees Fahrenheit, rather balmy, don't you think? And what we're learning now is the surface composition is actually including both nitrogen, carbon monoxide, methane, ethane traces, and based on the density measurements we're seeing, we think that this body is actually almost a little bit more than a third ice. And that would include a lot of water ice. And if you've heard the story, follow the water, because we believe that's the key ingredient that would enable life. Lo and behold, we're finding an awful lot of it out there, even as far out as Pluto. And lastly, the atmosphere of Pluto, which it does have. Right now, our intrepid spacecraft is doing measurements on the Pluto atmosphere as we speak today. That's what its task is. And it turns out it is an amazing thing to study with loads of information that will help us in our understanding of our own atmosphere. So, little known fact. Pluto has 5 moons, not 1. And I think it's really fascinating that 2 of those 5 moons we had not even discovered when the New Horizons spacecraft was launched. We didn't even know they were there. So that's kind of interesting. We're going to study things that we didn't even know were there when we launched. There's always surprises. And there's a very interesting gravitational resonance between Pluto and Charon that we've discovered. It turns out they both have a day that lasts 6.4 Earth days long. But they're in 100% gravitational synchronization, which means they always have the same side of each other facing each other. So as they rotate around, they're always seeing the exact same part of the other body. So it's very unique in the solar system, to say the least. We haven't found any other examples of that. There are 5 of them out there. Notice the discovery dates. The first one, Charon, we picked up from a ground-based observatory, and that was in 1978. And I'm going to show you the picture they used to find it, and you're going to be hard-pressed to find it. It takes a well-trained eye, to say the least. Nixon Hydra, 2005. These were all Hubble Space Telescope pictures. And then Styx and Kerbetros were done actually after New Horizons launched. These are not large bodies, which probably means, gives you an example of why we didn't see them before. They're actual diameters. And by the way, this is late-breaking news, folks. This is courtesy of New Horizons as of Monday night. That first number right there, it turned out we were off by about 50 miles with our best estimates. The exact number is 1,473 miles. Thank you very much. $700 million to get the spacecraft out there, and there's our data. But Charon, as you can see, is about half that size, and the other moons are literally as small as 4 miles wide. And yet we can see them, which I think is pretty amazing. 3 billion miles away. So let's talk about Pluto. Today we have fancy CCD cameras, and we have computer systems that can do thousands of these images in seconds. But Mr. Clyde Tombaugh back in 1930 had photographic plates. And he did what they used, it was an instrument called a blink comparator, where you'd put one image up from 2 days ago, and then an image from today, and you'd blink back and forth really fast. And you'd be staring at this thing, and if anything moved between the 2 images, you'd see it jumping. And that's how you found planets and, well, comets and just about anything else. And you did that manually. And you did that all day long, every day. And that proves that astronomers are very dedicated to their job, don't you think? This is what Clyde saw. These are the actual photographic plates. And I don't know about you, but I can't pass an eye test for the DMV, and I'm really struggling. But the arrows help a little bit. If you'd like to see this, I can show it to you on the computer later. But those 2 little arrows are pointing at a little dot that moved in the 2 images, and that was the first discovery of Pluto. That's how it was done, folks. So let's kind of advance time. As Brian mentioned, it was an 85-year history of this discovery. That's how we found Charon, that blob. That was a ground-based observation from 1978, a very large telescope, by the way, and that's the best we could do. And oh, by the way, did I tell you that image is enhanced? Enter the first whiff-pick camera on the Hubble Space Telescope, and we got a much better picture, don't you think? I'm kind of thinking if I had that picture, I'm calling Time Warner Cable to get them out to my house to fix it, okay? But that's the best that the Hubble Space Telescope Whiff-Pick 1 and 2 could do. Then we put Whiff-Pick 3 in. Thank you, Space Shuttle. We were able to put a whole new camera into that telescope in space, and look at how much better that picture is. And boy, the new moons kind of pop right out at you, don't they? So that's why we went up to service the Hubble Space Telescope, guys, because now we can get some much better pictures. But if you think that's good, there's nothing like being there in person, and that's what New Horizons did 2 days ago. So this is going to run a time lapse of what we saw from Clyde's original image all the way up to our present day. And are we going to be able to get that video to run? There we go. Now watch carefully. This is it coming into focus. And of course, that's the image from today. Amazing. It's 85 years of history right there. So let's talk a little bit about how we got there. The New Horizons mission. That is the actual launch of the Atlas V rocket that took New Horizons out to Pluto. It was launched in January of 2006. It has the world speed record, or should we call it the intergalactic speed record of any spacecraft launched from Earth. When it left Earth's gravitational field, it was moving at 36,000 miles an hour. We've never sent a craft up faster. Why did we do that? Well, because if we wanted to get the data back within our lifetime, we need that thing moving fast, right? So she was really booking. Interestingly enough, this is what we mean by rocket science being hard, guys. When the last engine stopped, that was all the propulsion we had. She coasted all the way to Pluto. So if we blew it on that last burn of that last engine, there's no hope. And I love this analogy. Getting this craft on the right trajectory to Pluto was like landing a jumbo jet airliner on a tennis ball without a pilot. Because after all, you can't direct this thing when it takes 4.5 hours to get a radio signal to the craft. So it's got to do it on its own. So land that jumbo jet by programming it in advance, sending it to China, and landing it on a tennis ball. That's about the equivalent of what we just did. Apollo, when we went to the moon, it took 3 days for our fastest, largest rocket to get to the moon. New Horizons got there in 9 hours. It got to Mars by April, Jupiter a year later, Saturn a couple of years later, Uranus a little bit more, 3 more years, Neptune 3 more years. You're starting to notice how much further these outer planets are. And we got to Pluto 9.5 years later, traveling at those speeds. 9.5-year mission. That's a long way. And we couldn't have done it without Jupiter, because we stole a little Jupiter's energy by doing what we call a gravitational assist. We got 9,000 extra miles an hour out of Jupiter. Thank you, Jupiter. We didn't have to pay the bill. I told him to put it on the tab. And people ask me, what does that mean? That 9,000 miles an hour saved 5 years off the total trip. 5 years. So thank you, Jupiter. And when we actually got to Pluto, for a number of reasons, periodically we turn the spacecraft around so it can point its antenna back to Earth. We lose energy when we do that. It actually encountered Pluto at 31,000 miles an hour, and we were 7,750, to be precise, miles above the surface of Pluto when we crossed closest. So I'd call that pretty good aiming, don't you think? Pretty good aiming. There's our Intrepid spacecraft, and my friends at JPL were kind enough to send us a 3D printed model of the spacecraft. I thought I'd hand that around for you guys to take a look at it. But that's what she looks like. Interestingly enough, it's about the size of a grand piano. The rocket ship that sent it up there was 200 feet tall. The actual spacecraft was about the size of a baby grand piano. And that big antenna is 83 inches wide, so it's a very large antenna. It's almost as big as the whole spacecraft. That's what it takes to get a signal back to Earth, right? And she was about 1,000 pounds at launch. She had 170 pounds of propellant that's used to orient the spacecraft in flight. And all of the science instruments combined were 66 pounds. That's it. By the way, that rocket, when it was sitting on the launch pad, 1.5 million pounds of rocket takes 66 pounds of science instruments, 3 billion miles. That's rocket science, folks. How about this? This is incomprehensible to me. The total amount of power available on this spacecraft is less than 2 light bulbs. So it does all this science and takes all these amazing pictures and beams them 3 billion miles back to Earth, works for something on the order of 15 years without fail, and it does all that on 200 watts of electricity. That's rocket science. And then we've got the 16 hydrazine thrusters we talked about. So I'm not going to drag you guys through the detail here, but I like to call this the honeymooners episode of spacecraft science instruments, because the first one's called Ralph. And the second one's called Alice. Bang, zoom, right off to the moon with you, or Pluto in this case. Basically, these instruments were designed to do a number of things. Primarily look at the atmosphere, the composition, what is Pluto made out of, take really good pictures to get geology and topology of these bodies, and beam all that information back. There was also, for the first time in history, we sent a student-designed experiment up. And the students from the University of Colorado designed an experiment that measured all the little impacts that hit the spacecraft on its 10-year mission. And you might say, well, that's interesting. You certainly want to know what's happening so you can build your next spacecraft better. But it turns out this design was done to see if there were rings around Pluto, because we found rings around on a bunch of planets, right? It's not just Saturn. And we're wondering if there are rings. And oh, by the way, Mission Control was really scared of those rings, if they were there. Because when you're moving 30,000 miles an hour and you hit ring particles, it's a bad day. So the last 2 days, Monday was the last time that New Horizons talked to us. That was our chance to redirect its course in case we found something that it was going to hit. So there's one of our newest images. We call it the heart of Pluto, because if you see that white area kind of down at the bottom, it looks like a heart, almost. So we've already found some interesting things. We've been able to exactly measure the size and mass of Pluto and its moons, and also the historical geological processes are quite interesting. It turns out these worlds are very much alive. There's a lot of geology going on every day. And one of the effects we think that's causing that particular heart, the atmosphere on Pluto literally freezes right out. When Pluto goes further away from the sun, the nitrogen atmosphere, now that should be interesting because our atmosphere is 79% nitrogen. Pluto is mostly nitrogen atmosphere, and we think it freezes completely out and just falls onto the planet when it gets too cold. So it creates some very interesting geology, to say the least. We also are not seeing a lot of impact craters in those smooth areas. Now, this is a 4 billion year old or 4.5 billion year old object, and it doesn't have a lot of craters. That tells you something happened, right? One of the jobs that we're working on right now is to figure out what that something was, what's causing that geology. We see all these modeled regions, and oh, by the way, we see hills, we see valleys. On Charon, we found a valley that is larger than the Grand Canyon. So we've got some very interesting, this is not just a rock in space like an asteroid. It's a very interesting place. The atmosphere, as I mentioned, is even more interesting because what we learn about that atmosphere can tell us a lot about our own planet and the history of our own planet, because it turns out our atmospheres are very similar, and we didn't know that. We're also looking for complex organic molecules, and we're finding a number of carbon molecules already. And that's interesting because Kuiper belt objects include comets, right? Like Halley's Comet, short-period comets. We've measured them, and we found complex hydrocarbons in them, very complex, like precursors of life complex. They come from the same region of space that Pluto's in. So if we can learn more about Pluto and what's on it and what isn't, we get a clue as to the origins of life. And of course, back to that debate on is Pluto or isn't Pluto and all that stuff. And I welcome that debate. I think it's fantastic. But what's going on here is we are now defining the archetype of what a Kuiper belt object really is and what it isn't. And why is that interesting? Well, I think it's fascinating that the word planet is the only scientific definition we had of what a planet was for like 3,000 years. And you know what planet means in Greek? Wandering star. Somebody said it, wandering star. That was the scientific definition of planet until 2006. I don't find that very scientific, do you? Who had to get involved in this situation. Well, once we went there and we can characterize this object, now we're going to have an archetype that we can use to measure all the others. So there's our moon Charon, and from the picture you can immediately see the hills running through kind of the center region of the moon. Those are actually 600 miles long in that picture. So we've got some mountain ranges, and it also suggests very strongly that those combined with that blackish sort of area on the top, active geology on Charon, the moon of Pluto. So what's next? Well, we're going to make sure that our spacecraft is healthy and happy, and I'm happy to report as of right now, she is. And we're going to be doing all of our measurements to find out what the gravitational fields of Pluto and Charon and the moons did to our craft's trajectory. Because remember, we don't have engines, we just have thrusters. So we got to figure out where we are in space. That's very important. The first thing we did was turn the craft around, beam a beautiful picture back to Earth. And then we turned it and aimed it right at Pluto so that the sun and Earth are behind Pluto. And we're currently beaming a very high-power radio beam all the way to Pluto. It's passing through Pluto's atmosphere, and the craft is measuring the results so that we'll get a composition of the atmosphere from those studies from the spectrometers. By the way, just synchronizing that event was quite a challenge, to say the least. We're also doing, in addition to the atmospheric measurements, we're doing measurements on the solar wind at Pluto, because there's some really dynamic properties in the atmosphere that Pluto's atmosphere is burning off into space, and we want to find out why and what's replenishing it. So we're measuring that now, and of course, 16 months worth of data is going to come back to Earth. Pending an extension of this program, we would like to send New Horizons off to another Kuiper Belt object. So we're waiting on the Congress to decide whether they're going to fund that. And in 16 months, we're going to have a treasure trove of information that's probably going to take us the better part of 100 years to analyze. So it's been an amazing, amazing mission. I like to put this chart up just to show you the relative distances. So if you look at this, you can see that Earth next to the Sun has got the 1. That's 1 astronomical unit. This is not a linear chart, by the way. So you can see Pluto is about 40 times further away from the Sun than the Earth is. But the nearest star, if we want to go there, is quite a bit further, another 500 times further. And it took us 10 years to get to Pluto at the fastest we've ever been. So a little bit of idea of the scale of this mission. To quote my friend Steve Jobs, one more thing. That's what Pluto looks like up close and personal. That's the latest image returned last night, in fact. We call it the new part of Pluto. It's 100 million years old, but it's new in geologic terms, right? And we're looking at essentially a mountain range that's 11,000 feet tall. Makes Mount Everest look like a bump. And that's what we found on Pluto in high resolution. So lots more pictures like that to come.
How about a nice round of applause for Sean Bale with that introduction to Pluto? And so the rest of our program will be Q&A, and Katie and I have microphones, and we ask that you get our attention and let us bring the mics to you. So yeah, let's start off right here.
With all the new technology and so forth, anything that's going to have a commercial application come out of this mission?
Commercial applications. The answer is undoubtedly yes. I'm not exactly sure what they're going to be, because you usually don't know that going in. Almost everything that we're doing here is science. It's basic science.
66 pounds of scientific instruments. I can't get cell phone coverage this good. So, I mean, there's got to be something there.
Well, you know, you mentioned communication systems, and actually there is a major advancement in communication systems that the New Horizons spacecraft is using, and it's a series of error correction codes and the like for getting high volumes of data back over long distances where they're being transmitted with, 10-watt transmitter. So to that end, yes, this has definitely proven out those techniques without a doubt. Might help you with your cell phone coverage in a little while.
Mm-hmm. One thing you might be thinking of, one thing that I picked up is that for a lot of spacecraft, brand new instruments are designed and built. When this one got approved, they had to build it from start to finish within about 4 years, and it was a really short period of time, which meant they depended a lot on technology that already existed. So it was making the best use of, rather than starting from the scratch, they were putting together components, some of which were tried and true, cutting edge, tried and true, but ready to go.
Yep. Well, to kind of dovetail on that, the main processor, you go down to Best Buy and buy a computer, and they're talking about how many gigahertz the processor is. The main computer processor on New Horizons is 12 megahertz. 12 megahertz.
Now,
why?
Which is a fraction of the speed of anything we have.
That's
probably
correct.
In our phone. So why would that be?
Because if it breaks, you don't have a repair guy 3 billion miles away. So we use the ultimate reliability machines. So they spend more energy and more time and design work on building redundancy into the processor than building speed in. Because once again, there's only one of them, and if it breaks, $700 million went down the tube.
And these things have to withstand radiation,
Yep.
particles of various kinds. One of the things I just wanted to toss out, just because when you say it's going like 30,000 miles an hour or 32,000 miles an hour, but just because that's a hard to grasp number, that's nearly 9 miles per second. That's how fast it went by Pluto. So if it went by you in 1 second, it would be about 9 miles away. That's how fast we propelled it.
That's right. And if you run into something at those speeds, it can be a really bad day. So all of the components and all the circuitry is rad hardened and then double rad hardened and hardened on top of that to try to protect it. So speed is not what's important.
They mentioned Tuesday that they went through a moon's orbit to clear out the dust, and I thought that was interesting.
Well, I mentioned earlier that we were looking at a potential ring system, and if you've got moons, and you probably have really, really small moons, which would be like grains of dust and the like. So we certainly expected that, and remember, that's what the University of Colorado kids were designing, was something to count the number of impacts and get an idea of how big they were, so that we can get a better idea of the constituents of that region. But you don't want to run into something so big you're dead, right?
We have a question over there.
Hi. I was interested in if you could tell us the correlates in Pluto to the two fluids that we have on Earth, that is water and air. Would you expect to see anything like dust storms caused by an air-like fluid? And would you expect to see any large movements of the surface mass caused by something that can move more momentum like water could? So that's the question.
Wow, so a great question, and that's probably one of those 20-minute long answers. I'll try to answer it this way. The question is about the constituents of the atmosphere and if there's water and the potential for water to move on the surface and adjust the surface, right? The topology of the surface. And we absolutely see that. That's what we're seeing with these canyons. It's probably not flowing in the water that you and I know. It's probably more glacial because it's all ice. It's so cold. But we're absolutely seeing evidence of those kind of processes, glacial properties of ice. And it's not just water ice. It's actually methane and carbon monoxide that's freezing out. So they become solid, but they can still move under the right conditions. So yes, we're absolutely seeing those processes. Carbon monoxide, yes. We've also got ethane. We found ethane as well. In the atmosphere, you mean? Mostly nitrogen, a little bit of carbon monoxide, a little bit of methane, and a little bit of ethane that we've measured so far. The question is, what about the nature of the atmosphere and the constituents? What I will say is that Pluto's atmosphere is extremely weak. It's about 50,000 times less strong, if you will, less dense than Earth's atmosphere. And there's another really interesting property that we just found out from New Horizons data, and that is that the Earth has only one compound, water vapor, that can sublimate between solid, ice, and gaseous, right? We only have one on Earth. But it turns out when you're out at Pluto at those temperatures, there are three. Nitrogen can freeze right out of the atmosphere. It goes straight to snow. So nitrogen snow, if you will. That's kind of a cool thought. And then also you've got the methane. So it can transition all the way to solid. And we don't have any evidence of that so far. It's solid to gas, sublimation type relations.
How fast does Pluto rotate on its axis?
on its side is 6.4 Earth days per one rotation.
So I had three questions, real quick ones. But one was, if it's going 30,000 miles an hour, how can it still be studying the atmosphere? So I just need perspective. The other was, I was interested a little bit in the plutonium dioxide that I guess is its power source, and an explanation a little bit about what that is and how it was to handle that.
Okay.
And I forgot the third one, so just...
Wow, I breathed through that third one really quickly, didn't I? Got that answer right. If it's going 30,000 miles an hour, your question was, how do we do studies?
How could it sample how could it make that?
Sampling the atmosphere now.
Okay, great.
And I thought it just passed it in 9 seconds.
Right. That's the relative velocity of the craft at closest point of approach, right? That's that number that we keep quoting. But what we're doing is we turn the craft around, and now we're rapidly departing Pluto. So we're pointing all the instruments back at Pluto. So the relative velocity is still very high, but we're getting a stable image right in front of us. Okay.
Can we be studying Pluto?
It's going to be on the order of about another month.
Okay. And the third question is what was it sending back to us for these past 9 years? Anything?
Most of the last 9 years, it was asleep. It would wake up periodically to say, hey, I'm alive, do you have any new commands for me? And by the way, it's very traditional. We're constantly sending new commands. Some of them are course corrections, so we're going to adjust the trajectory a little bit. Some of them are, we've actually reprogrammed the computer to do whole new different things, because to your point, we're learning the whole time. So we may send up new commands and new command sequences to make it more efficient at doing what it does. Save a little energy, for example. We do that all the time. Now, as far as the official term is radioisotope thermoelectric generator. That's the power source for this craft. A lot of people ask me, why do you have something with 12 syllables in its name? The answer is, there's no solar energy out there. The solar energy that far out is actually significantly less than a 200-watt light bulb. It's like 1.5 watts. So that's not going to work. There's no other power source that works well. But it introduces, as you said, plutonium-238, plutonium dioxide. First of all, it's not weapons-grade stuff. All right, it's not. It just isn't. And secondly, it's embedded in a ceramic substrate that prevents it from, were there to be, for example, an accident on launch, that ceramic substrate prevents the plutonium from, shall we say, aerosolizing, which is what you're really worried about. This particular isotope of plutonium only really has alpha particles, and the alpha particles can get stopped by a sheet of paper, right? They're not super high energy. So what you're worried about is some of that stuff getting in the air and somebody breathing it. So we've solved that problem by putting it in a ceramic substrate, so it's going to break into pieces, large pieces. You're not going to inhale it. So the actual study, and NASA does a massive study on this for safety purposes, they said over 50 years there would be 0 incidence of cancer or other catastrophic human ailments given a massive failure at launch. So we were very careful about that.
That's in the first 50 years, but you didn't ask him about the 51st year.
That's correct.
That's when all the cancer kicks in.
I hope not.
Now, I'm right. I think that along the way, New Horizons did make a few observations. There was something about some observations of the smaller red spot on Jupiter. And Jupiter does, as Sean mentioned, all those outer gas planets have rings. We all know Saturn's rings, but they all have ring systems that are just less visible. And Jupiter has a very faint one. So there were a few, mostly asleep, but a few other observations.
You're absolutely right. When we went by Jupiter, we were relatively close to get that gravitational assist. Well, if you're close by, take a few pictures, right? It's like traveling all the way to the Great Wall of China and closing your eyes and going to sleep, right? So we woke up and we did a lot of good science at Jupiter as well. And we took some pictures of Saturn, and we're still very interested in Io, which is that ultra-volcanic moon around Jupiter. So we took a lot of time, lot is a relative term, but we took a lot of time to study that. So, did I get all three of them?
So I agree that 7,700 miles is really good, but if NASA could have gotten ideally as close as it wanted to be, what would have been like the target? And I heard that when the spaceship passed through the Kuiper belt, even the tiniest things could pierce the body of the vehicle.
Correct.
and that what it was going to do was turn itself so that it used its its
big antenna
as a shield. Is that true?
That is true. There were several contingencies. As I said, Monday night was everybody thinks that as you pass by, all the scientists are huddled around their machines. They were actually all out having a beer. The job was done, the craft was on autopilot. But Monday night was that time where we had taken all these pictures of where we were going, and if there's something really bad in our way, we were going to either change the trajectory of the craft a little bit, or worst case, if we felt, wow, there's a lot of ring out there, we would turn the whole craft around and make that big antenna go in front as a shield, and it's armored. I mean, armored, again, is a relative term, but it's armor-plated relative to the body of the spacecraft, and we have some experience. Again, we learn as we go. Cassini out at Saturn, when we got to Saturn, we did the same maneuver where we turned the big antenna in front of the Cassini space probe, and we flew right through the rings of Saturn. And we did get hit a lot. I've listened to the audio tape, and it sounds like a hailstorm. And the hail particles were grains of sand or smaller, but there were a lot of them. And that antenna, Cassini just went right through, no problem. Except for the heart attacks that were occurring with the engineers. Yeah. True story, it's a $3 billion spacecraft, and we didn't know for sure it was going to make it through. So, yes.
Now, but Cassini in orbit around Saturn wasn't traveling nearly as fast, as New Horizons.
This was on orbital insertion. So it was
slowing down.
It was slowing down the whole time. Retro rockets were firing right before then, but it was still doing thousands of miles an hour. Yeah. Oh, yeah, the 7,750. Really complicated question because we're not just looking at Pluto, we're also looking at Charon. We get too far away from Pluto, we're getting better Charon. We want to balance between studying both because, again, it's a binary system, really. And on top of that, we wanted to have the highest, or should we say the least probability of running into something. So we were plotting a trajectory that was the safest course, not necessarily the best scientific course. So when you go and listen to these mission meetings beforehand, I mean, the scientists want to be like right there. And the engineers are going, you're going to kill my spaceship, right? Don't do that to my spaceship, right? So there's always a healthy debate between.
Lots and lots of data, great distance. There's bound to be error in the capture of the data and its transmission and its reception. You said something about this actually at the beginning, but I'm wondering what kinds of steps, I presume this is some sort of mathematical or statistical steps, are being taken to deal with the inevitable error?
Great question. And again, back to your first question. What's your internet speed at home? A couple of megabits a second, something like that? Yeah, back in the days where I was just getting out of diapers, we were doing about 12 kilobits per second, right? That's what New Horizons is transmitting at. Very, very low data rates. On top of that very low data rate, there's a huge amount of what we call error correction information that's added to the signal that mathematically will allow you to recreate the actual data. So we're adding redundant information into the data stream. That redundant information allows us to fix the errors. Because you're absolutely right. There are huge numbers of errors when you're transmitting that far away with a 10-watt transmitter, because that's all we've got to use. On top of that, we don't transmit the data once. We transmit it like 15 times. So we do it over and over and over again. So this is part of the reason why it takes 16 months for all this data to come back to Earth. A, there's a lot of data, yeah, but B, the transmission back, it's not that it just takes a long time to get here, it's that to get it here correctly without the errors takes a lot of work. So.
Sean?
Yes, sir.
So if you guys never shot up the New Horizons mission and you only shot it up sometime this year with modern technology and you didn't know what you knew about Pluto kind of thing, how much more efficient could you make the spacecraft in its computer, in its energy sources, and its science equipment?
Fantastic question, because technology moves fast. You're absolutely right. I'd give you an example. of what we're doing with the Space Launch System, which is the new major rocket for the U.S. That's its name. We come up with really fancy names, right? Space Launch System. Must have been an engineer that named that thing. But nonetheless, you know, third graders name most of our space probes. That we actually do put a contest out there, and it's third graders, and they come up with really cool names like Curiosity, and we've got Space Launch System. But back to your question. The answer is about 20%. So from shuttle days to Space Launch System, we're getting about 20% more propulsion efficiency. And if you look at major technology initiatives within NASA, propulsion is number one on the list. Because you saw that chart about how big space really is, and you know, I want to get there in a lifetime. So you need to go faster or be more efficient. And we're learning things like with ion drive propulsion that we've used to get our spacecraft to Ceres, which is in the asteroid belt. So on average, call it 20% from space shuttle to today.
Excellent. And in case you've forgotten, I'm now at the table where I have this vantage point. While we're all taking in all this information, we have the poets here that are taking it in and synthesizing it into poetry. So work is happening right here.
Brian, I hope I didn't say anything that's going to get me in trouble. You know. Oh, yeah, uh-oh. My wife is in the audience, so please be gentle, okay?
Will NASA go ahead and select the next phase, the next object that it's going to look at before they hear from Congress if they're going to fund it, just so that they've got I know that there's a limit as to the navigation fuel, and the earlier they make this course correction, the wider the angle that they're going to be able to explore.
Absolutely true. So that process has been going on for the last 5 years. The scientists are debating with the engineers what's possible, what isn't possible, what's cool, what isn't cool. And then all of a sudden, Hubble finds another cool object, right? And then the debate starts again. So this has been going on for 5 years. So we've already got a whole bunch of candidates listed out. And to your point, time and money become part of the issue. If you wait too long, you'll never be able to turn around and go back. The good news is the Kuiper belt is 2 billion miles wide. And we've already estimated that there's about 100,000 objects so far. Now, we've actually been able to take pictures of a few hundred of them. Actually, it's about 1,000. But we estimate there are at least 100,000. I'm guessing, even at the speed of Congress, we're going to be able to get to one of them. No offense to any politicians in the crowd.
Hi, so I'm going to come back to the communications question again and ask, is convolutional encoding any part of what you were talking about?
It is, or the family of codes known as convolutional codes, yes.
What is convolutional coding?
It's an error correction code where, again, it's the same thing I was talking about. It's one of the techniques that's used to add information into a signal, you know, digital bits, if you will, that you can then deconstruct, you know, the errors out of, just pull it out of the signal.
Why would that even be your question? That was the kind of, so are you an electrical engineer or a?
I have a master's degree in computer science, and 20 years ago when I was at NC State working on my master's thesis, my advisor had a whole team of people working on convolutional encoding and got a patent for it. So it's something I heard a lot of, and it sounded very familiar.
Absolutely, that's what we're...
I want to know if NASA owes your friends any royalties, patent payments,
Yes.
So I'll have to refer that question to our attorney, sorry.
And I think we have another question.
We are using those kind of codes.
Yeah, Sean, another communications question. Who's receiving the data? What organization? And is it worldwide or is it strictly U.S.?
It is strictly U.S., but it's in partnership because it turns out we use an operation called the Deep Space Network. These are those monstrous antennas that you guys have probably seen, you know, in pictures or what have you, and they're all over the planet. So we have to have partnerships with the folks in Australia or, you know, wherever that are running those antennas in order to make it possible. But they're the only antennas that can actually grab a signal from that far away. Another interesting tidbit of information: there's one man-made object further out than New Horizons. Anybody know what it is? Actually, there's two. Voyager, which one's further out? Well, it's 50% chance here. Raise your hand if you think it's Voyager 1. All right, raise your hand if you think it's Voyager 2. The twos have it.
So Voyager 1 was launched first.
And it's not as far out.
And Voyager 2 is farther. But what about before the Voyagers? There were the Pioneer 9 and 10.
We can't talk to them anymore.
Oh,
They're
but
dead.
don't we have an idea of where they are? Or
Well, that's a good point. My guess is that they weren't moving anywhere near as fast because they didn't have the gravitational assist. Like Voyager 2 got assist from every planet it went to, so that's adding huge amounts of speed to it.
And correct me if I'm wrong, because you may read some contradictory seeming things in articles where you'll hear this was the fastest, that New Horizons launched with the fastest speed, but it's not going to catch up to Voyager 2 because the thing that I haven't seen any articles say it, but it's Voyager 2 is moving faster than New Horizons. It wasn't launched with its highest speed, but it did more gravity assists, so it picked up more. And I haven't really seen, heard that somewhere from NASA, but most articles haven't been clear on it. So you might see this weird contradiction. It's like, well, you said it's the fastest, but now you're saying that's the fastest.
Well,
it launched faster than anything we've
without
ever
a
launched.
doubt. And the speed has been changing plus and minus the whole time as, again, we rotate the craft and it's going to change its dynamics relative to the Earth, for example. But this is like the story of the fish that got away, right? Mine's faster than yours. So you can imagine going out for dinner with some of these engineers, and it's usually in a heated debate. But back to that original question, we still talk to Voyager 2 every single day through the Deep Space Telescope network. Every day, its transmitter is 1/10 the power of New Horizons, and it's on the order of many, many, many tens of millions of miles further out. So I think that's an amazing accomplishment, just to have a craft that we can still talk to that has left the building. It's out of the solar system.
Yeah, and you know, how often are we supposed to get our automobiles maintained? Every 20,000 miles or something, 3-4 billion miles, no maintenance, launched, and good luck, right?
Well, yeah, like I said, a lot of crossing your fingers and hoping everything works out right.
So, Sean, this has been fantastic. I think we only have time for about 2 more questions here, possibly 3, and then we have our science poets. So, here we go.
Hi. You're doing all this, 66 pounds of research mechanisms, communications on the power of 2 light bulbs.
Yes.
Is there any possibility, or can you speculate on the possibility of translating this efficiency to everyday use of energy?
Well, I can certainly speculate that NASA has some really good scientists and engineers, and I think that comes back to the first question we had tonight, which is we learn from all of this. Most of us interact. Your cell phones wouldn't be possible without the space program. Most of the technology that we have today, microcomputers and microchips and the whole thing, that whole branch of engineering wouldn't exist had it not been for NASA. So to your point, yes. What's really neat about these things is going in, you never know which one's going to become the next big thing, right? So you break frontiers, you do new science, you do new engineering, and you always wanted better, cheaper, faster, right? So a lot of our new probes are done that way. We're trying to get more for less money spent. I don't know if you saw the Spirit and Opportunity landings on Mars. You guys have probably all seen like big rockets that have retro rockets and they come down and land and all that. We didn't do that to save money. We did airbags. So we got it down to 200 miles an hour and then just dropped the thing on airbags and prayed the airbags didn't break, right? But that's the kind of engineering that we're studying, and every time we get better. Curiosity is a different example, but what we learned in the prior times, we were then able to land a 1-ton spacecraft on Mars at negative 0.1 meters per second. Negative. It was actually slightly coming off the ground when we dropped it.
Sean.
When the spacecraft was going past the planet and doing all its measurements, there's tons and tons of movement that the spacecraft is doing. Obviously, the instruments themselves aren't moving; the whole spacecraft is moving. What kind of was that? First of all, was that all pre-programmed, or is there any? And was there any provision made for in case something went wrong? If it got off by a millidegree, would everything be lost?
The answer is yes, everything would be. So we spend months and months and months running the computer simulations with all the what-if scenarios. So again, space flight is kind of like this. We've got 9.5 years to get there. We wake up every 6 months to say, hey, am I okay? And during the next 6 months, you're programming whether or not you're going to make any changes to prevent that exact scenario. The next thing is that on board, the craft is fully autonomous. So it knows there are star trackers on the craft that point in every direction around it. And it's got internal maps of where all the stars should be. And it's taking pictures several times a second. And it knows if its orientation is off, so the craft is programmed to fix that. Now, the very worst thing in the world that could happen is you're actually in a course or attitude change maneuver when you take the picture, because then you get to smudge. That would be the worst thing to happen. So now what you've got is the interrelationship between the cameras that are actually taking the pictures and the attitude control thrusters that are orienting the spacecraft. And then we've got reaction wheels that are basically big gyroscopic units that are keeping everything stable. So that 12 megahertz processor is doing all that on 200 watts while it's taking the pictures and running the whole spacecraft.
And all of this has to take into account the time lag for signals going back and forth. And I also understand that, you know, when this launched, and especially before it, we have that precise location for Pluto.
We didn't even know its mass. We were off by 3%. 3% off means you missed. It's like, oops, I got to Neptune. I meant to go to Pluto, right? 3% is big at 3 billion miles away. So, yes.
I noticed that a lot of the pictures that we have seen have been very, how should we say, bright. And I was just wondering, I've had a little trouble with the exposure time of the cameras and what it says on the website with regard to exposure time of the optics. Could you tell a little bit about the units of the exposure time for the cameras?
Well, I can certainly say that you have to leave the aperture open for longer than you would normally, because you're talking about, there's a great app. If you guys go out, go to nasa.gov and look for Pluto time. And this is going to, it feeds directly into your question. How much illumination is there on the planet, right? Because that's really the question. And it turns out, it's a great story that the very brightest it gets on Pluto, at the brightest moment of the day, on the strongest day of the year, when it's as close to the sun as it'll ever get, is about the very beginnings of what we would call dawn. Right before the sun pierces comes over the horizon. That's the brightest it will ever be on Pluto. So for the photography buffs out there, that's the kind of environment you're taking pictures. But it gets worse, because coming inbound, we've got the bright surface, quote unquote, right? Everything's relative. You're coming in and seeing the bright surface, the sunlit side of Pluto, right? As soon as we turn around and we're on the other side, we're going back this way looking at Pluto from that angle. Now you know what's illuminating Pluto? The reflected light from Charon. So build me a camera that can handle relatively very, very bright to very, very, very dim, and be able to have the aperture set properly and the exposure levels. And you even see that with Hubble images. That one I showed you of all the moons, you can see clearly the Pluto is giving you that just saturated image. So then you have to put all this not error correction, but you have to put these algorithms to work to try to strip out all the artifacts that are being added, because you've had to saturate part of the camera to get the rest of the image, right? So again, it's a balance between all the above. But the folks that do the algorithms are amazing. The pictures that we see today. Think about what happened with Hubble. You know, the original Hubble went up with a bad mirror, right? And look what we were able to do to fix those kind of images.
Well, Sean, we have kind of reached the end of the program. I'd just like to ask you a final question. Like, were you particularly excited about this mission compared to other missions? I mean, there's a lot of exciting stuff. And in fact, here's a little bit of context, because ever since the space shuttle fleet retired, people kind of think that was the end of the American space program. And it was the end of something significant, our ability to launch astronauts to the space station. But it's not even close to the end of the space program where we have so many other missions going on. But was this mission particularly exciting to you? And whether it was or not, what excites you the most about New Horizons?
Wow, great. Well, the answer is yes. This was one of the most exciting missions we've had because it's breaking so many firsts, right? First time anything's ever been to Pluto. First time we've ever seen a Kuiper bottle object up close. Engineering that we've talked about has many, 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 many firsts. So whenever you got all those firsts, plus a little bit of patriotism, it's all about go NASA and go America, right? That gets me really excited.
Yeah, because we were kind of upstate. The European Space Agency just landed
Rosetta,
on a comet. So we really had to come back with something,
Gotta
didn't
come
we?
back strong, yeah.
We can't let them outdo NASA.
Hey, we cooperate, but we also, friendly competition makes us all better, right?
Yeah.
But to your other question about NASA and just exploration, I like to say that mankind has learned more about the universe and our place in the universe, our history, how we got where we are, so to speak, in the last 10 years than mankind had learned over the prior 50,000 years. So at that pace of knowledge expansion...
To be sure, those first few thousand years, I don't think we figured that much out.
Fire is good,
And
right?
all that did is get in the way of our stargazing.
Yeah, that's right. Yeah. Turn out the fire, dude. I can't see the stars. But seriously, I mean, the pace that we're going at, and NASA currently has space probes and craft at every major object out there. We're putting up a new one that's going to be taking daily full-color images of Earth, and that's for Earth science, right? So it's not that it's really the end of anything. It's always the stepping stone to the next major discovery. And I think that's what just keeps my interest from the time I was 9 years old till now. There's always something really cool around that next hill, right? There's always something. Look at this. I mean, when we launched New Horizons, we didn't even know about all those moons out there, right?
Yeah.
When we accidentally went by Enceladus at Saturn, it was an accident. We happened to snap this picture, and we see a geyser coming out the bottom of a moon. And we're like, wow, that's cool. And then we sent Cassini in and found out it's water. It's really water, and it's salt water, and it's got complex hydrocarbons in it. And then we're saying, geez, wow, that's kind of what we think the Earth was like when life was just starting, and we just found it on a moon, right? So this is the kind of stuff that's happening every day at NASA. How can you not be excited?
Yeah.
Right?
So, and now, Sean, I know you have some things out here.
I do.
So, but before the program ends, let's get our poets to come on up on stage. Sean brought a bunch of handouts. So at the end of the program, you'll be able to come up here and get some handouts. Right now, Sean, I'm going to let you stand down for a second. How about a nice round of applause for Sean Bale?
Thank you, guys. Thank you very much.
Sean, don't go too far away, and when people come up here, they'll want to ask you some more questions, but I want to turn the stage over to in fact, well, one microphone will be enough. Let's have our poets come on stage. All right. So just to recap, we've worked with these poets. It's not always the same poets, but Pam brought this idea to us, Pam Taylor, and the group is called Living Poetry. How many poets does this involve?
We're over 600 poets in the Triangle, just 4 here today, but we are the largest poetry meetup in the Triangle.
All right. So, as we said, now, not that they didn't have any thoughts in their head regarding Pluto before they came here, but the idea was, and the challenge to them, which they wanted to take on, was to be inspired by tonight's program and write poems inspired by the program. So we're going to start with Kelly. All right. So Kelly Lennox, and her poem is called King of the Dwarfs. And I'm going to ask you to hold the mic close and project.
And I want to thank Brian for the wise advice.
Is this the start of your poem?
No. Just holding the microphone does not confer amplification onto you, he said.
Yes.
And I want to add that I've never done this before.
Poetry or speaking into a microphone that confers
writing on the spot and
writing
reading
on the
in
spot.
public.
Excellent. Maybe you should have saved that afterwards to see if it didn't go, hey, I never did it before. All right, so Kelly Lennox with King of the Dwarfs.
The furthest we've ever been, and you don't quite rate. Say some, but we are making history together. Planet X, discovered by mistake. You break all the rules. Laid back, you turn space on its side. Dance with Neptune and do-si-do with Charon. The two of you never turn from face to face in a double star formation that didn't make the final cuts. 10 years ago, your moons appeared. 9 years ago, New Horizons launched. In the fastest launch ever, we don't want to die first. 8 years ago, it greeted Mars. 7 was Jupiter. 4 years since Uranus, and 1 year past Neptune. Our piano-sized eye is winking at you, measuring your heart and guessing at what built your bones. In Pluto years, I am 1/5 and would bring a heat wave to your array of ices. For as long as Earth turned, you and partner Charon have been erasing craters, for Charon too pushes up its ranges of ice mountains. The Kuiper belt of wandering stars is a place in space showing steps on the path to life. Our science departs into rings of dust.
Kelly Lennox, everybody. Next up, and it's been quite a long time, but she's been with us once before, Alice Osborne with Plutonic Theory.
No yellow king of the underworld, no judge of the dead. No Mickey Mouse underworld either. I am king of the dwarfs, who makes my own mountains with a 1,000-mile heart. Ignored for years by you earthlings. Good thing I'm not codependent. I read Lovecraft to up my orbital energy. Time is a flat orbit. When you flew by me, you missed my ice glaciers, my ice geysers, paving over my young, hot, searing craters. You missed my whole other side with bunnies, rainbows, and transformers living in the rainforest among the tree houses as the volcano explodes. Ha, just kidding. Give me new expectations. Thank you.
Thank you, Alice Osborne. And Angie's been with us for a lot of these poetry readings. So this next one is Stranger in a Strange Land by Angie Kirby.
Here, there be monsters raising their heads, Kerberos and Hydra with 10 between them. The eyes don't bear counting. We kept ours down until, in a blink, you were there, flying. A blurry buckle in Kuiper's belt, a shining accident already happened. In a third of your year, the time it takes a crocus here to grow, bloom, die, we were convinced you were family, the last child. Then we consigned you back to the night, our outer reaches. You kept your own charted path moving past us, above the sun, below it, not even listening to the whispers billions of miles away. Your heart stuck to a spot that we finally saw glistening, a forgiveness. Our note is being passed to you by a friend. We like you now. Do you like us? Your answer, ice and air and life. Well, it's ingredients. We see you now. We're sending a present. the ashes of one who took you from invisible to there. Let him sleep in your craterless methane sea, frozen until the time the spark that found us finds you. Wake him with your frozen clouds melting to free us all from our underworld made new.
Thank you, Angie Kirby. And Pamela, just before your poem, tell us where people can find out about Living Poetry, like online.
Sure, you can visit our website, livingpoetry.net, or join our meetup group, Living Poetry.
All right, so our final poem, Pamela Taylor with New Horizons meets Planet X.
Let's make history together. Explore the last rocky body in this solar system. Let's break all the rules, incline our orbits, spin on our backs while Sharon washes. Feed me your data in bits and bytes as we shimmy in front of Neptune to soak up the sun. I don't see any rings around you, so maybe we can make a new moon or two. I've looked past the Kuiper belt, seen through to your heart, whose beat fans the flames of your solar winds. My wandering star, my king, this mission is not over.
Thank you very much. Pamela Taylor, Angie Kirby, Alice Osborne, and Kelly Lennox. And Sean, come on back up here, Sean. The inspiration for our poets, Sean Bale, once again. And so if you want to talk to Sean, he'll be up here. And like he said, he has some great handouts from NASA. And thank you very much. Give us some feedback on our feedback forms. And I already told you we have some great programs coming up. And this building is still open until 9 p.m., so you don't have to go home. But thank you for all your great contributions. And good night. We'll see you next time.